We're going to take a qualitative look here at colligative properties of solutions, and as your notes packet says, that these properties depend on the number of dissolved solute particles in a solvent. And there's some calculations you could do with this, like to calculate the change of boiling temperature and freezing temperature, but we're just going to take a peek at the qualitative aspect. So first up, when you put a solute into a solvent, and again we typically talk about water being our solvent, the boiling point of that solvent will then go up. The solution has a higher boiling point. And you can see here I typed out for you that we learned that boiling occurs when vapor pressure equals the atmospheric pressure that's pushing down on the liquid. Vapor pressure gets lowered because the solvent particles are busy doing their dissolving of the solute. They're solvating the solute particles. And like I said, with water, they're hydrating it. They're pulling them apart, breaking it down, and so a lot of the solvent particles are busy doing that. Well, so now it's going to take more energy to get the solution to boil, because you have to take that energy and get the solvent particles to get away from the solute, and then also go ahead and turn into a gas. So perhaps somewhere along the line you've cooked noodles or seen someone cook noodles, spaghetti on the stove, and oftentimes they put salt into the water. And really the only reason you do that is for flavoring, because if someone ever says, oh, well, I'm going to put salt in the water to make it boil faster, it's wrong. You're actually taking it longer to boil because you're putting a solute into the solvent. Now, it's very insignificant. You would need to put a lot more than just a sprinkle of salt to get a significant change in the boiling point, but nevertheless, it is slightly elevated. On the flip side, the freezing point of the solvent, the solution, goes down. So when a substance is freezing, a nice orderly pattern is being created. We saw when we talked about water, that nice honeycomb-like pattern is created, which makes water expand when it freezes and ultimately float. Now if a solute is present, then that lovely pattern is disrupted, and the water molecules are moving around much more, so there's more kinetic energy involved, so we have to remove more of the kinetic energy in order to get the solution to freeze. This is why we put salts on the road at winter time. Now, the salt only works at certain temperatures, but 32 degrees Fahrenheit is when water freezes. So if the roads are 32 degrees Fahrenheit, then we can have the snow or freezing rain freeze on the surface. However, if we put the salt down, then we create a salt water solution. And when that happens, that solution has a lower freezing point than regular water, and so the roads will have a liquid solution on them instead of frozen water, even at temperatures below zero. Again, it has a cutoff point where it actually works, so if it's 25 degrees below zero outside, they won't salt the roads because it doesn't work. Perhaps you've seen at the stores, or you've used calcium chloride, the little pellets. It's called heat. Calcium chloride actually works a little better than sodium chloride when they spread that on the road, and that's going to have to do with a dissociation factor that I'll talk about here in a minute, but just keep that in the back of your head. Another place you might have seen this is if you've ever made homemade ice cream. This container here, you put the ice cream, the cream and sugar and liquid into the center, and then around it you put ice. And then you shake it up and get it to work, or get it to freeze. Well, pure ice doesn't work that well, especially when you start shaking it, the ice begins to melt pretty quick. So you typically have to put rock salt in with the ice, and that drops the temperature of the ice and ultimately ice water that's surrounding, and so you get the ice cream to form much better that way. So the last little thing here is what we call a dissociation factor. And as I mentioned, I hinted at the difference between calcium chloride and sodium chloride when it comes to putting salt down to get rid of snow and ice. Again, the colligative properties depend on the number of dissolved particles. So yes, if you put a sprinkle of salt in water, the boiling point will go up. If you put a cup of salt in water, it'll go up more. But also it depends on how many particles the solute will break apart into. If you remember on your water world test, this was the written part you had to turn in. You had to show me how a solute dissociates into water. So sodium chloride, for example, here has a dissociation factor of 2. Because when you put this in water, it breaks apart into the sodium plus 1 ion and the chloride minus 1 ion. Calcium bromide has a dissociation factor of 3. It breaks into the calcium plus 2 ion and 2 of the bromide minus 1 ions. And so again, this is why if you've seen that melt or the heat or whatever, calcium chloride has a dissociation factor of 3 compared to sodium chloride having a dissociation factor of 2. So it has a more dramatic effect. It lowers the freezing point of the saltwater solution even more. So that's why it would make a more effective de-icer, if you will, when used in that purpose. Calcium sulfate. This has a dissociation factor of 2. Calcium plus 2, and our good buddy sulfate stays together as a polyatomic ion. Same thing here with aluminum sulfate. 2 aluminums and 3 sulfates. So this has a dissociation factor of 5. Now sugar here, C6H12O6, glucose, has a dissociation factor of 1. In fact, all molecular compounds have a dissociation factor of 1 because the molecules don't break apart. The solvent breaks the solute down to the molecular level, but it doesn't actually take the molecules apart. Now, another place besides salt on the road and stuff that we see the colligative properties of solutions at work is in your car. Okay, your car has a cooling system. Essentially, some pipes run around the engine and draw heat away from the engine, and a liquid passes through the pipes, absorbs that heat, and then the liquid goes into your radiator, travels through all these little tubes, and as the wind passes by the radiator, cools the liquid back down so it can go around the engine again and absorb more heat. Well, water made an excellent coolant back in the good old days when engines didn't run so hot, but also we had a little problem. If you used water as the coolant around here in Mentor, Ohio, well, during the winter when the temperature gets below freezing, the water would freeze, it would expand, and it would crack the pipes, crack the radiator even. And so what we end up having is antifreeze coolant that's put into the cooling system. Alright, so antifreeze, well, as you see here, it allows the cooling system to operate at a greater temperature range. It has a much higher boiling point, so it won't boil away and cause your engine to overheat, and then it has a much lower freezing point, so it won't freeze and expand and cause damage. So yes, even on a very hot summer day, 100 degrees outside, running on the highway, you won't see, like perhaps you've seen in the movie or in real life, where the car is overheating because you just had water in the cooling system and it starts to boil and the pressure builds up so much, poof, it blows off the radiator cap and causes the car to overheat. All the water escapes as vapor. It almost looks like a geyser. Alright, and then the last thing in your notes packet there just says, what's another fluid that you might have noticed that also obeys these rules in your car, and that would be windshield wiper fluid. It's usually blue in colors, most popular. Sometimes it's purple or pink even, but it's a solution. So even when the temperature is well below zero, as long as those little jets aren't clogged with ice, then you can still be using your windshield wiper fluid because it has a freezing point that is much lower than just pure water. Alright, I hope that helps, and good luck on your test.